el trabajo que va a presentar o la exposición que va a hacer Joaquín es bastante didáctica y clara, con lo cual no creo yo que pueda aportar mucho más al tema. Solamente recordaros que Joaquín lleva con nosotros relativamente poco tiempo, todavía no ha cumplido el año, proviene de la Universidad de Southampton, donde acabó el doctorado el año pasado y donde ya trabajaba en dispositivos fotónicos integrados con tecnologías de silicio. Aquí se ha incorporado al grupo que intentamos tirar adelante y que básicamente se centra en el desarrollo de una plataforma fotónica de nitruro de silicio para aplicaciones en el visible, y parte de esta plataforma también os la va a presentar hoy, aprovechando la ocasión que le hemos brindado, bueno, que le ha brindado Sabela y el IMB de hacer esta charla. Joaquín, cuando quieras.
Muchas gracias, Carlos, por la introducción. Bueno, pues comenzamos. Voy a cambiar al inglés. So basically, good morning. So my name is Joaquin Faneca, and today I'm going to talk about the tunable silicon integrated photonics based on functional materials. This is a work that I have been developing between the University of Southampton, the CEPER Institute, the CNM, and the CSIC. So the introduction to the talk, basically, first of all, I'm going to give you an index. So we're going to talk about the silicon photonics, then we will move to silicon nitride technology, then the different materials that we are using to make them tunable. Then I will go through the different devices we have fabricated and tested. So 1D photonic crystal based on liquid crystals, a silicon-rich graphene modulator, and then some integrated photonics using non-volatile materials. Then we will conclude with the talk. So first of all, silicon photonics. So why is silicon photonics important? Yeah. So basically, silicon photonics is the optical analog of the silicon microelectronics. So silicon photonics was emerging due to the fact that electronics was having some drawbacks. And these drawbacks were that they were limiting the speed and the bandwidth of the data. So they talk about the silicon photonics as the technology of the next generation communication. So basically, they are low cost, this technology, and is CMOS compatible. So basically, they were moving to silicon just because they were exploiting the microelectronics fabs. You can see big companies like Intel or IBM that they have already some products in the market of silicon photonics. So Intel here, they talk about silicon photonics of the technology that can move data using light, basically. And IBM, which is silicon photonics, is the future of high-speed data. Also, in this slide, I wanted to share with you like the forecast by BEOL Development. It's a statistics study. And here what you have basically is like the development of silicon photonics in 2020 and the forecast in 2026. So you can see here right now, the most investment in this field is in data center transceivers. So most of the devices are transceivers in this case, or long-haul transceivers as well. You have some 5G transceivers, but you can see that the main device that we are exploiting in this technology right now is the transceivers. In future, in 2026, we expect to invest even more money, $1.1 billion, but we will move to, for example, a big area in consumer health. Also, you can see here, this red one is photonic computing. This means that quantum computing and neuromorphic computing will be inside this category. We will still keep the fiber optic and the data center communication, so we will have still transceivers, but you can see that the future will move to consumer health and also photonic computing. So silicon photonics, as I said, is the CMOS photonics, a technology of next generation electronics, but they will coexist together because you will need to move from one to the other. You can have intra and inter-chip interconnects, lab-on-chip systems, high-performance computing, or environmental sensing. This is some pictures from IBM. So you can see here an off-chip optical traffic. So you have optic fibers here. This is a routing. So this is the chip, integrated circuit. When you route the light, you have memory layers and you have processors layers as well. This is a wafer scale fabrication process, and you can take out these chips individually, which are really small, even smaller than a coin. But everything is not fantastic in silicon photonics, otherwise we will not be here. And we have some challenges to sort out. And one of them is that silicon has an indirect bandgap. So that means that we don't have light emitters directly in silicon, and there's a critical problem right now. So people, they're integrating 3-5 components in order to achieve the light on chip sources. The transparency of this silicon at telecommunication wavelengths. So I mean C-band and O-band, which is 1550 nanometers and 1310 nanometers. These telecommunication wavelengths, the silicon doesn't detect light, it doesn't absorb. So we don't have directly detection with silicon. We need to use materials like germanium. Also, it's a centrosymmetric crystal, so that means no Pockels effect modulation. So for create modulators, people has done this kind of devices, which you have PN junctions, and with the voltage, you inject carriers, and then what you do is with the gating, you create a shift in the devices. So you're able to have tunable devices with the PN junctions, but not directly with the Pockels effect. Then the silicon is thermally not really stable, so you can have a problem in temperature stability. And the high index contrast, so the refractive index of the silicon compared with the silica of the optic fibers, has difficulties in the coupling. So that means that you will have losses when you pass from the optic fiber to the chip. Then we will go through the silicon nitride technology. So why are we using silicon nitride and why is this useful? So first of all, an overview of the European open access silicon photonics ecosystem. So we have SOI, that means silicon manufacturing. Okay, so fabs that do silicon. So we have IMEC, LETI, VTT, IHP, and Cornerstone. Silicon nitride manufacturing, which is Cornerstone, Lyonics, IMEC, Legentech, CNM, ourselves, we are here in the nitride one, and the rapid prototyping, which is Silicon Photonic IC, AMO, Infotech, and Cornerstone. So we're here, and then if you go to this web page as well, you can find more details about the platform that we have been developing and running here. We have already run some multi-project wafers, and we are now in the 5th one, and it's a really useful integrated platform. So we were talking about as well with the European Silicon Photonics Alliance, which are basically the limitations of the current devices, no? And here we can see that the light sources as well is something that is really challenging because it's not established either in silicon or silicon nitride in larger scale integration. I mean, so you can have some specific companies like Intel that they can have some light on source, but it's not like larger scale integration. You cannot have access. It's not an open access boundary. Then we will focus basically in the challenges here of the phase modulation. So you can see that the modulation here thermally is really power hungry in silicon and really power hungry as well in silicon nitride. So basically it's a problem of the energy consumption. And also a challenge as well is that it's not established is the non-volatility. So devices that they consume the energy only when you switch them, that's all. You don't consume energy when you want to maintain the state. So these two are the ones we are targeting. So we're targeting phase modulation and non-volatile programmable functions. The rest of the problems as well are there, and probably in future we can target them as well, but we are focusing these two right now. So silicon and silicon nitride, basically, optically talking. Silicon has a high index contrast. That means that the bigger is the refractive index, the smaller is the devices you can do. So basically the footprint is smaller. The nonlinear effect is big in the silicon with good grating couplers, but the transparency, as I will show later as well, is not as big as the silicon nitride. So here you have transparency in the near infrared. You have 2 photon absorption at telecommunication wavelengths, which is limiting the nonlinear effect. The multilayer stacking, you cannot make 3D integration with crystalline silicon, so that makes difficult the scalability in 3D integration. It's really sensitive, the silicon, due to the fact that the index contrast is bigger. What it happens is that a small change in the width of some geometry of the building blocks or the roughness itself affects a lot the mode, affects a lot the phase propagation. And the losses that we are talking about here in silicon is around 1-2 dB per centimeter on the waveguides. Instead, silicon nitride has a really good transparency. You have no 2 photon absorption at telecommunication wavelengths. That doesn't mean that if you go down to visible range, you will not have TPA. That's really important to notice. You have multi-layer stacking, which means that you can have different layers, one on top of each other in 3D. It has low loss, 0.01 dB per meter. This is really tricky as well because that depends on the geometry as well. So when you have this small loss, means that your geometry requires a big bending radius. So that means that the footprint of the device will be big, even though you have really low losses. The refractive index tunability, that's a really good thing that silicon nitride possesses, which is the deposition control. So you can control the deposition and you can do nitrogen-rich silicon nitride, silicon-rich silicon nitride, or stoichiometric silicon nitride. So basically, you're able to control the refractive index and control what is going on the waveguide. It's really good for nonlinear effects. So the nonlinear effect, as I said here, the silicon one is better than the silicon nitride, but the problem are the losses of the nonlinear effect, the nonlinear losses. The nonlinear losses of the nitride are better than the silicon, and that's why silicon nitride is a really used material in nonlinear integrated optics. The index contrast is not as good as the silicon, and the grating couplers needs or require more complex designs in order to achieve the same losses as the silicon one. So the footprint compared with the silicon is a bit bigger. So to sum up, the refractive index contrast in silicon is high, in silicon nitride is low. The integration density, why I put here high, low, and high, low. Okay, if we talk about one layer, so one layer of silicon or one layer of silicon nitride, the integration density will be high in the SOI because the index contrast means that the footprint is small. But if we talk about 3D integration, one layer on top of each other, silicon is low. The other way around in the silicon nitride. So if we talk about one layer, the silicon nitride is low, but if we talk about multi-stacking, in silicon nitride is high. So the scattering loss is high in silicon, low in silicon nitride, the barrier is the same. Wavelength range, as I mentioned, near infrared only. With the silicon nitride, that is the one we use, we can go through different ranges, visible range, near infrared, and mid infrared. Both are CMOS compatible, and the two photon absorption at telecommunication wavelengths, which is important to point out, has some effect in the SOI, but not in the silicon nitride. So how I see the roadmap here. Okay, so when I started the PhD, okay, I was reading, and everyone was talking about the photonic integrated circuits. People were using different materials, so gallium arsenide, indium phosphide, silica, silicon, silicon nitride, lithium carbide. Why the people were moving to silicon photonics? Yeah, so then people were selecting silicon photonics just because they were able to be compatible with the electronics. So the fabs were able to use the machines and the tools in order to fabricate the devices. So that means that they didn't have to change the process law. So you don't have this step until you see something in the market. So until the market was not demanding that this photonic integrated circuit should be in silicon in order to reduce the costs, we didn't have this movement. When we established the silicon photonics waveguide, so you can see here how the optic fiber is coming and the waveguide is guiding the light. Basically, you have passive devices here. So you demonstrate that the silicon or silicon nitride can transfer light from one point to another. The next step was, and that's where I was working as well, is in tunable active materials. So that means that you should have this tunability. You should be able to tune the waveguides. And that's where we started with the functional materials. And the next step and the final step that people is targeting right now, or the next step that we need to target, is the programmable silicon photonics. What does it mean? That means that you have here a computer, okay? And from the computer, you should be able to control what is happening on your chip with the light. So you should be able to select the path that the light needs to follow on your chip. And to have a programmable silicon photonics, you should have a software defined. You should have a flexible chip. That means that it should have different functionalities. You should be able to upgrade the program as well. And you should have something smart. So when you talk about the smartphones or smart TVs, yeah, you're able to interact with your phone, you're able to interact with your TV. So that's the same. You should be able to interact, and the chip should be able to have some knowledge about what is happening and as well correct some errors. Okay, so the functional materials that we're using. So we're using liquid crystals, graphene, and phase change materials. That are materials that are tunable. Why are they different? So liquid crystal is a continuous tuning. So you have really low power consumption when you tune them. They are volatile, CMOS compatible. They are really slow when you switch them. This is a really important point, microseconds or milliseconds. I'm saying slow because in telecommunications, you need to go nanoseconds or picoseconds. So sometimes if you talk about biosensing, some of the guys will say that microseconds or milliseconds is really fast. For communications, it's really slow, to be honest. Then you have electrical switching. You can switch them electrically, or you can switch them with a laser. So basically, silicon nitrides require tunable materials for low speed photonics. So maybe if you want to tune a laser, you know, like you need something that is not really fast. So this is where the liquid crystals can converge with the silicon nitride. The graphene one is compact, is volatile, CMOS compatible. So when we were collaborating with Cambridge, they were doing 6-inch graphene depositions. Switching times are really fast, nanoseconds. High broadband, you can move from different ranges of the spectrum in communications, and you can switch them electrically as well or optically. The graphene normally is used as a modulator, photodetector, or heater. And then we have the PCMs, the phase change materials, which are non-volatile materials. They are really fast, they are CMOS compatible, they can be switched optically or electrically, but the drawback here is that it's really difficult to control the intermediate states. That means you have different states and it's really tricky to come back to exactly the same position. But they have a really high optical contrast. As you will see, this is really important for modulators in photonics, and they are used for making switches, memories, or phase modulators. Okay, so for all of you that you don't know anything about this, so basically this is a waveguide. So you have the light going through a waveguide on your chip. So you have your input signal and your output signal. So what we do, imagine this gray thing is silicon nitride. We deposit a material, some material that is functional, some material that can be tuned. And then with the input signal, what we do is we travel the light here and we interact with the material. We can have different situations. We can have amplitude modulators, phase modulators, or amplitude and phase modulators at the same time. What does it mean? Okay, the amplitude modulator means that you are just modifying the imaginary part, okay, of the refractive index. Refractive index is just an optical property of the materials. So when the light is traveling here and it reaches the point of the amorphous state, or whatever situation is the layer of the material, you switch the material to the other state, in this case, crystalline. And if you are having an amplitude modulator, you're just changing the imaginary part. So changing the imaginary part, that means you are changing just the amplitude, but you maintain the phase. Okay, so at the end, you will have an output with a different amplitude, but with the same phase. If you go to phase modulators, it's the other way around. You are just changing the real part of the refractive index. So you have the input, again, you interact, you switch, and you're changing the phase, but the amplitude still stays the same because of the fact that you're not changing the imaginary part of the refractive index. Okay, these situations, amplitude and phase modulators alone are ideal, almost never happens. So what it normally happens is you have both. You change your material from one state to another, and you change the real part and the imaginary part of the optical properties. So at the end, you are changing the phase and the amplitude, okay? I'm saying that because when you want to cascade different building blocks, when you want to do larger scale for neuromorphic computing or quantum computing, this is really important because you should be able to control the signal in amplitude and in phase. Then I'm going to move to the different devices that I have fabricated and tested. So first of all is a 1D photonic crystal based on liquid crystals. This is it. This is on silicon. So this is just 7 grooves. So these are silicon walls, and the dark lines are air. So basically you have 7 grooves of air. This is the chip, and here you have a cone shape. In the cone shape with a micro needle, you infiltrate the liquid crystal. The liquid crystal flows through the micro channels. And what happens is here, I have some walls, as you can see in this picture. And what it happens is I put the liquid crystal on the cone, it travels around here, and with the walls, I doesn't allow the liquid to go to channel 3, 5, and 7, either one. So the liquid is only going through channels 2, 4, and 6. That's why I put these walls here. And then I have contact pads here. So I apply with a probe some voltage and I tilt the molecules of the liquid crystals. What is happening here is with the voltage, you're changing the orientation of the liquid crystal. So you're changing the refractive index. So you're changing the optical properties. So this is what I was talking about. So you have channel 2, channel 4, and channel 6 with the liquid crystal. And then you modify one of them with the voltage. So this is just the setup. So you have the laser, goes through a polarizer, comes into the station with the optic fibers, and here is your chip with the proper station. This is the chip. This is the groove. The U-grooves is where you put the optic fibers. So these are the optic fibers. So the optic fiber will go here, and then you measure the transmission through the cavity, through here. What happens? So basically what happens is when you have the 3 liquid crystal channels with the same state, without any voltage applied, you have a triplet cavity, which is this one. You have 3 resonances, which they are coupled between them. And if you change the middle one with a voltage, what you do is that you transform this triplet cavity in a singlet plus a duplet. And the quality factor, you can see here, the sensitivity of this resonance is much higher. You improve by 2 orders of magnitude the sensitivity. So what you're doing here is you're able to control more or select the wavelength that you are working. And then you can tune these wavelengths. So here is just a video in which I I can just play for you to see what is going on here. So you can see how applying the voltage, this is a polarized microscope, I control the refractive index of each of the channels. This is channel number 2, channel number 4, and channel number 6 will be played later as well. So you can see in this video how I am able to control each of the channels individually. So this is basically how we are able to control, you see, in this case, each of the liquid crystals by themselves. Then I will move to graphene modulators. So here we're going to talk about the silicon-rich graphene modulator. So the state of the art. So first of all, Liu published in Nature the first graphene modulator and how that works. So that works that you are gating the graphene and you are changing the Fermi level. So if you have the Fermi level below the valence band, both valence and conduction bands are empty. So you cannot absorb any photon. If the Fermi level is between the valence band and the conduction band, that means that the valence band is full and the conduction band is empty. So you can absorb the photon. But if you have the Fermi level above the conduction band, both the conduction band and the valence band will be full and you will not be able to absorb any photon. So that's how it works, the graphene modulator. So the state of the art, we're moving and we were reaching 22 gigabits per second. Then Ferrari in Cambridge reaches 10 gigabits per second with an optical graphene modulator. And this is a theoretical one, and they were reaching 10 gigahertz, so 10 gigabits per second in this case, but it's a slope waveguide, so the light is traveling in the air. So for fabrication, this is really tricky and it's theoretical, but they have never proved it experimentally. What we offer here, what we were proposing here is, okay, we have different optic fibers with different signals. This is a grating coupler, so put the lights from off chip to on chip. So the light is traveling here in this waveguide, and I couple the light in each of the rings. So it comes here, and I couple the light here, and it goes out in this way. Depending on the dimension of the ring, I couple one wavelength or another. So basically you filter the wavelength with the dimension of the ring resonator, the radius. And on top of each of the rings, we put a graphene capacitor with a voltage. So you were able to control the amplitude and the phase of the signals in each of the outputs. So this is the mode, basically, how you characterize an optic waveguide is with the mode. So you can see that this is the absorption, the red one, and the blue one is the phase. So you can have different regions. What does it mean is if you see region 1, the absorption, if you change the Fermi level from this point to this point, or if you are more familiar with voltage, we can go through voltage. So if you have voltages between 0 and 4, you see that the absorption maintains constant. So you have 0.12 dB per micron, and you are changing the phase. So what will happen here is you have a phase modulator. You remember you have the absorption constant and you change the phase. In this region, in region number 2, you are changing both. You're changing phase and amplitude. And in region 3, you will change only phase without the amplitude. Region 3 is really interesting because you have no losses. You see, the losses are really low, 0.01. So you will have here almost a completely phase modulator. Here you will have both, and here you will have also a phase modulator, but with bigger losses, 0.12 dB per micron. So this is the response. So each of the rings has a resonance. So the resonances are here for each of the wavelengths. That is determined by the radius of the ring. And with the graphene, turning them on and off with the voltage, you can kill the resonance or not. So you can see you can have an on and off state. So combining all of them, what I was doing is, okay, each of the rings, so ring 1, ring 2, ring 3, if they are on, off, you can have different combinations. So all of them are off, you have 0, 0, 0, and the ring 3 is on, you have 0, 0, 1, and etc. So you can have 2 to the power of n being n the number of rings and number of combinations, basically. And the silicon-rich graphene modulator that we did, that I was showing as well, the energy per bit in the on-off, we're talking about 0.51 picojoules per bit. So this is just the length of the graphene modulator. So the LG here is just how it's changing depending on the length. Here you can see the length of the graphene capacitor. So of course, if you have bigger lengths, you need more energy to switch it. And what we were trying to do is, because we saw that the energy consumption depends on the voltage to the power of 2. So if we are able to reduce the on-off voltage, so you can see if we are able to have the on-off voltage 1 volt, that will mean that it's a really CMOS compatible technology and we will reduce a lot the energy. So that depends on the material that is between the graphene layers. What does it mean? Is in this case, in the graphene layers, we put silicon nitride as well. So this is silicon-rich nitride, and the material that we use between the 2 graphene layers is silicon nitride. If this material has a really low permittivity, you can see that with low permittivity, the voltage that you need from on to off is really big. It's almost 4-5 volts. But if you increase the permittivity of this layer, the voltage will reduce. The on-off voltage will be around 1 volt and the energy consumption will reduce. These are just the equivalent circuit electrically talking and the bandwidth. So we're talking about picoseconds here. And yes, the silicon-rich nitride compared with the stoichiometric silicon nitride, you can see how we can reduce the distance between the contacts. So ds is the distance between the contact and the waveguide. So we can reduce it with the silicon-rich because it has a bigger refractive index and the mode is more confined. So you don't need to have the gold as far as for the stoichiometric silicon nitride. So at the end of the day, what that means for if you don't understand a lot about silicon photonics is that the silicon-rich nitride can offer a higher bandwidth than the stoichiometric silicon nitride in this case. And finally, I'm going to go for non-volatile materials, so the phase change. Phase change, you can see the refractive index and the absorption for the different wavelengths, and they have a really big contrast in this range, which is at the communications wavelengths. So they have a big change in absorption and a big change in phase. So what we did is we design and fabricate this waveguide. So in the O band, which is 1310, they measure 900 nanometers wide, and we have 300 nanometers thick. And we deposit on top the GST, which is the PCM here, the phase change material, GST, 10 nanometers, and we cover it with 10 nanometer silicon nitride for avoiding oxidation. We did the same using the same platform, 300 nanometers thick silicon nitride, but for the C-band, 1550. The only thing that you change here are the dimensions. So the width of the waveguide here is 1.3 microns. Okay, you can see in both states. So this is the amorphous state of the PCM, and this is the crystalline state. Because the crystalline state has more losses, extinction coefficient is bigger, you can see how the mode compared with this one is jumping up. So it's interacting more with the PCM. These are the fabricated structures. So we have the rings, resonators, which are these ones, is a zooming image, or these are the waveguides. So this is the grating coupler, which you couple the light from the optic fiber to the waveguide, and then it goes here and it finds the PCM. So the characterization that we did, so for different PCM lengths, what we were doing is characterizing the loss. So you can see that for a crystalline state, you have 6.6 dB per micron, and for the amorphous state, 0.2. That's really important because that means that with 1 micron of PCM on top of your waveguide, you can have a difference in absorption of 6.6 dBs, you know? And this we characterize this for the different wavelengths. So you can see there is some dispersion in the crystalline state, and the amorphous is more flat in the O band. And then the rings. The rings are the resonances, basically. So without the phase change material, you have the dashed black line, which is the resonance of the PCM without any absorption. Then when you deposit the amorphous state of the PCM, you have a shift in the resonance because you are changing the phase. And you have here the black line. And then when you switch it to crystalline state, the absorption increases a lot and you kill the resonance. So this is a zoom-in image of this one. So if it's in amorphous state, you have the resonance. If it's in crystalline state, you kill the resonance. So basically you have a switch here, a switch that is 11 dB different. So an on and off state. And the same for the C-band, basically. We did the same for the C-band, but the problem or the difference here is that the change in amplitude is much smaller in the C-band than in the O-band. But you have the dispersion, which is much more flatter in this case than in the O-band. Here, the extinction ratio is bigger. You can see we were talking about between the off state and the on state of around 18 dBs. And I will move also to the O-band and reach Mach Zehnder. So we did a Mach Zehnder interferometer. That means is you have the input light here, you split the light in two, and then you combine it here. So you have an interference. If you put the material on top of one of the arms, you create here a change in phase and in amplitude. So what you are doing is you are able to tune, you are able to change the interference pattern. Okay, so basically you have your input, you split it in two, light is going here and here because there is a different path. You come here and the interference. The interference here, you can basically control it with the state of this material. This is an SEM image, so you have the Mach sender, and here is the GST, the material. So basically here is the response of the interference in amorphous and the crystalline state. So you can, as I said, you can control in both states the resonance. The resonance in this case is the interference pattern. Okay, if we talk about rings is resonance, if we talk about the Mach sender is interference pattern. So these are the device losses that, of course, the amorphous state is smaller, has lower losses. So the crystalline state is the red one. So you have losses of 0.87 dB per micron, and in the amorphous state, 0.064 dB per micron. And the extinction ratio, which is the difference between the amorphous and the crystalline states, is increasing with the length due to the fact that with the bigger the PCM, the bigger the phase change material, the more losses you have. So this red pattern comes down and increases the difference with the black solid line. And basically these are all GST, what I said, which is all amplitude modulation. And in this case, I'm going to talk about phase modulators. So in this case, SB2, S3 and all this stuff is just for changing in phase. So there is no absorption, as you can see. And they are non-volatile, have a wide bandgap because you don't have absorption in the telecommunication wavelengths. So you can have only phase modulators. We did the same. We deposit these new materials, the SB2, S3 on top of the Mach senders. This is in the amorphous state, and these are in the crystalline state. So we have A is SB2S3 and B is SB2SE3. But these kind of materials are materials that are low loss, basically, in both states. What I mean is that these patterns, you need to understand much more about this, but basically the patterns here, what they have is, you can see this is amorphous state and this is crystalline state, and they maintain the same extinction ratio. That means that the losses are really small, which is really important for the community due to the fact that we are finding low loss materials that they are non-volatile in both states. So the losses you can see in this case in the crystalline state are really low. Here the same. You have a big change in the phase, the effective refractive index. So to sum up and for you to have a clear knowledge about that, about the different materials that we have used in the PCM. So we have GST, which has absorption, and SB2S3 and SB2SE3, which doesn't have a lot of absorption. So you can see here the losses in the crystalline state, 6 dB per micron. And in this case, we have reduced by 6, even more, the losses. So this is a really big improvement for the community. And the delta NF, the change in phase, is bigger in GST and GSST than in these two. What does it mean is that for achieving a pi shift in the waveguide mode, you will require less length. So this is the length for achieving a pi shift in the phase. So the length for these materials is much smaller than these two ones, as you can see, 9, 7 compared with 13 and 21. But the important thing is the essential loss that you add to the system when you are doing this pi shift, because the essential loss is 62 dBs here, 10 dBs here, which is unconsistable to cascade more components. And that's why here these two are important, because even the length is bigger, the loss of one component is 0.39 or 1.68 dBs, which allows you to cascade different components for neuromorphic or for quantum. The same in the C-band, okay? So basically the loss, you can see how much smaller it is, and the length is a bit bigger than these two ones. So basically, if you want to have amplitude modulation, GST and GSST, if you want to have phase modulation, SB2S3 and SB2SE3. If you combine them, you can have both. So basically, you can have on-chip sub-wavelength Bragg ratings, and you can create a Bragg wavelength filter, tuning the crystallinity as well of the PCMs. And these are one of the devices as well we were doing. So you have a Bragg rating that here is coming, and you create a defect here. So you create a Fabry-Perot cavity, which is this resonance. If you put the GSST here, you can have it on off as well. You can control the resonance. And for finishing, this is what we have been doing here in CNM. Since I came, we designed some waveguides and some building blocks in the visible range. So when I came here, we were starting with that. And what we did is we were developing the the setup as well. So we have designed this, we have fabricated already. So we have the grating coupler here to couple the light from the optic fiber to the chip. This is an MMI, so basically it's a splitter from one input to two outputs. And this is the measurements we have been doing downstairs. So this is a single mode optic fiber, an input, and here you don't have any laser coming in. So this light is going through the waveguide, okay? The same here. Here is more clear. I put the optic fiber in, I couple the light, and I have a splitter here with two outputs. So basically, I hope that you know now why silicon photonics is useful, about silicon nitride technology, the importance towards programmable integrated circuits, which are the different functional materials that we can use, how are we using in different technologies in different devices as well, and why it's important to cover different ranges from visible to mid-infrared. So thank you so much for your attention.
Thank you, Joaquin, for the presentation. It was really good. And nothing, now we go with the Q&A. So if anybody has any questions, now it's the time to ask them. We have the chat, you have your microphones, you can turn them on. We have Joaquin here, we also have Carlos, so don't be afraid to ask them anything. Okay.
Hi, Joaquin.
Yeah,
well,
hi.
I am Cecilia.
Hi,
well, it was a really nice presentation, and well, it really, in some points, complicated for the people that is not used to these technologies. But well, you see a lot of possibilities for working with different kind of devices, and in my case, I am thinking on sensor devices and biosensors. So with the last structures you have developed here in the CNM, do you think that you are able now, you are prepared for developing some kind of biosensor using these structures? You have planned some line like that, some sensor, some kind of sensor?
This is a really good question, Cecilia, and basically yes. The answer is yes, but it depends on what the sensor is about. So I'm going to explain myself quickly. I mean, right now what we are able to measure is power. Okay, so what we measure is the optical power. In order to measure the phase, you need to have like an OSA, an optical spectrum analyzer. Which we don't have. You should have a tunable laser as well, which we don't have. And in the visible, it's really difficult to find it in the market also. So if you talk about a sensor that changed the absorption, so it changed the absorption of the light, we can. What we can do is just put on top of these waveguides here, we can have a trench. So here the cross section is easier. Maybe we create here a trench and we deposit here some molecules. And if they absorb at the visible range of optics, what you will have is in this output, you will have a change in the optical power. So this change in the optical power will be related with your molecules here. But right now, downstairs, what we can measure is power. So if you are talking about sensing with the optical power, yes, we can try to go for it. If you're talking about phase modulators or just biosensors that works with the phase, I think we are not ready yet to have them characterized.
Okay, thank you.
Any other question?
So hi, it's Cesar speaking.
Yeah, hi Cesar.
Hi Joaquin. So thanks very much for this very nice presentation. I had a question about these liquid crystals that you mentioned that can be used for modulating the properties of the silicon nitride, I think.
Yes.
For silicon photonic devices, and so it is just more from the chemical point of view that how easy are these liquid crystals to be integrated with the silicon photonics technology. You said that they are CMOS compatible,
Yeah, but in
yeah.
some companies they do it, but it's in-house, to be honest, what they do. So yeah, I mean, the thing is, it's not an easy thing to integrate. So what I mean is, first of all, when you integrate it with the silicon, you need to take into account as well the position of the molecules when they touch the walls of the silicon as well. So what it happens normally is that the liquid crystal, when you deposit it with a microneedle and you flow it, you have a determination of the positions of the molecules with the flow of the liquid, and at the same time, the ones that is near the sides of the walls, because of the forces that they have between the silicon and the liquid crystal, they orientate themselves towards the polishing of the wall of the silicon. So if the silicon has been etched and it has some direction in the crystal, you will have this directionality in the liquid crystal as well. But this position in the liquid crystal near the wall will be not the same as in the center. So you have kind of, let's say the liquid crystal near the walls can be like this, and along the channel are like this. So it's not as easy to integrate and easy to understand exactly the position of the molecules, but you can have a change in the refractive index at the end when you apply the voltage, because you tilt. Let's say you have you have an effective, let's say an effective area that you are changing. But it's not like you are changing.
And just another question.
Yeah, sorry.
Sorry, thank you. No, another question is, I guess that the possibilities are sort of endless with liquid crystals, because there are many different types of liquid crystals that you could apply here or not.
Exactly, and that's something I explored at the beginning, in which the thing is that I think there is more possibilities in the visible range, and because I was working in the telecommunications wavelength, the problem that we were having is that they were really slow. So if I wanted to use liquid crystals for datacom, microseconds and milliseconds are really low rates. So that was the only problem. But in visible, if you talk about sensing and all the stuff, this is not low. So there is plenty of things to do there, and this is something that it was emerging for communications, but they realized that they were really low. Now that we are doing sensing and we are moving to visible integrated circuits, I think they can be really useful for different, for example, for tuning the channels and select the channel for biosensing or something like that. It can be interesting to explore.
Okay, so thank you very much.
No, thanks to you.
Joaquin, this is Luis. Just a question. You have shown us devices with silicon nitride that were not known as stoichiometric. So you show some examples, silicon rich and nitrogen rich. This is just achieved by tuning the position conditions of the nitride, and how much can you change the refractive index, which is the window for.
Yeah, perfect question, Luis. And this is yes, changing the position basically is how we tune the refractive index, and the N rich. When I talk about, I should have put this, but when I talk nitrogen rich, we talk about a refractive index of 1.92, and then when I talk about silicon rich, I talk about 2.54. So basically, we're talking about a change in refractive index of 0.6, changing the position conditions.
Okay.
So it's a big change in the refractive index, changing just but all this is PCVD, it's not LPCVD. So that's why you have, I mean, you have this change, but that means that you pay the price of the defects inside. The defects inside means that you will have a big, more losses than with LPCVD nitride when you guide the light, basically.
Okay, and another question, the phase change materials that you show in the last slides.
Yes.
How do you put onto the wafers and pattern them? Which is just you evaporate them? Or?
Thermal evaporator, yeah.
Okay.
We evaporate them basically, and they are really thin layers. They are 10 nanometers or 20 nanometers, and we always need to cap them, otherwise they oxidize. So you need always to, when you use these materials, you need always to put some capping. You can use whenever isolator. So sometimes we use silicon nitride, silicon oxide, and you just need to have this capping layer in order to these crystallinities as well. You see, they will oxidize if you leave it in the air for more than 2 weeks or 3.
Okay, and you use die edge for patterning them?
If I use, sorry, say again?
Dry edge for making the pattern.
No. What we do normally is with the deep UV, you have your photoresist, you create the windows, and it's a lift-off process.
Okay.
Yeah, it's a lift-off process. So basically
Understood.
you deposit the PCM and then you do the lift-off, basically, yeah.
Good. Thank you, Joaquin.
No problem.
Okay, any last question? It's almost 20:01. I don't see anything on the chat or any raised hand. So it's your last chance. If not, you know where to find Joaquin and ask him later. No? Okay, we'll close for today then. Thank you, Joaquin, for giving the talk. Thank you, Carlos, for the introduction. And that's it for today. Next week is the NIT de la Recerca in Catalonia, so check the dissemination activities there are in Barcelona and everywhere. There are a lot of things, and we also participate in one next Wednesday in the Residencia de Investigadors in Barcelona, where USTRS will talk about open source hardware and RISC-V. So thank you for coming today and have a good weekend. Bye.
Bye, thanks.
Goodbye.
Bye.
Thank you. Bye-bye.